Okay, we'll be doing question 67 on page 51 of the college physics textbook by Sirway and Fogna. So, the question states, I've written it out here for you, is a stuntman is sitting on a tree limb. He wishes to drop vertically onto a horse galloping under the tree. The constant speed of the horse is initially 10 meters per second, and the man is initially 3 meters above the saddle. Alright? So now that you have this information, we should go to question A. So this is a two-part question. Question A asks us, what is the horizontal distance between the saddle and the limb when the man makes his move? So what does that mean? Well, that's basically telling us is how far is the horse from when the man jumps off of the tree so he can land on the horse. So for that information, we're going to need our for that information, we are going to need our we're gonna have to pick a kinematic equation. I'm gonna move this down one. I'm gonna move this down here so we have some space to work with. So there are several types of kinematic equations. The one we will be using today, if you have your AP Physics 1 equation sheet with you, the one we'll be doing today will be the change, wrong one, is the change in x equals the initial position of x plus the initial velocity of x multiplied by time plus 1/2 of the acceleration x of t squared. So this is all good to know. This is the equation we'll be using for basically this whole question. However, we need to actually understand what is going on here. So I think we should probably draw a little diagram. So what do we know? What's useful here for the first one? Well, this is asking us the horizontal distance between the man and the level of the saddle, right? So the answer to that right now, the horizontal distance between when the man jumps and the horse galloping. So we would have to try and find the change in x. So what's the change in x here? So the change in x would be the initial 3 meters above, because he's changing 3 meters. So this would be the initial time he's jumping off of it. Then we need to know that he's dropping vertically. That is an important information to use because he's dropping vertically, which means he's probably under the influence of gravity. So, and we also have to say that he's sitting on a tree trunk. Sitting, which means that he is at, wrong one again. He is at 0 meters per second. 0 meters per second. So, what does that information give us? Well, let's just draw a quick diagram here. I'm just gonna use a car in place for the horse because I really can't draw. So if we just do something like that, maybe, and let's just say let's have our man represented by this dot right here. So this man, we want to try and find that. Oh, you know what? Let me just do that in a different color. We want to try and find that. This is what we're trying to find. I'll label that as F. This person, this distance between here and here is 3 meters. 3 meters. Okay? So, he is at initial velocity of 0, and this thing is traveling at 10 meters per second. Well, I think the best way to go about this is what is the horizontal distance between the saddle and the limb of the car. Well, we know that when the car arrives here, that when this man jumps off, we get a time here if we actually calculate the influence of gravity. So I would suggest that we use the kinematic equation up here in order to calculate the time it takes for this man to go jump on here, to jump from here to the car, which would mean that we could actually calculate the distance in reverse by multiplying whatever that value is of t, well, because we're trying to find the time here, in order to try and find the actual answer to A. We'll multiply the value of t by 10 meters per second to actually get how far is the man away from the car. It'll make more sense as we go along. And of course, I forgot to move this question down more, taking up a lot of room. Okay, so what do we know? Well, we know that this is negative 3 meters, right? So if this is, come on. If this is negative 3 meters per second, if it's negative 3 meters per second, then this has to equal, if you look up here, the initial is 0, plus the initial velocity is also 0, multiplied by t, which anything multiplied by 0 is 0, plus 1/2. Now, what is our acceleration? Well, like I said before, we are falling vertically. We're falling vertically, which means that we're under the acceleration of gravity, which, since we're using meters per second, would be 8 meters per second squared. Let me highlight that really quick. Let me use a different color. Okay, so since we know that much, so now we know this is negative 9.8 meters per second squared. You know what, I need to move this over one because this is getting, the equation's getting a bit large now. 9.8 meters per second multiplied by the time squared. We don't know what the time is, we haven't been given the time. That's what we're trying to find out, because this will give us what f is, as we see. So now we're just going to do a bit of algebraic manipulation. This cancels out, that cancels out, that's nothing. So now what we want to do is we want to move the 2 over. Yes, we want to move the 2 over because this is multiplying everything here by half. So then this becomes, so we want to move this over. So multiply both sides by 2. And we get negative 3 multiplied by 2. I'm going to leave everything in a constant. I'm going to leave everything. I'm not going to simplify any equations like that. I'm just going to leave negative 3 multiplied by negative 2 as the answer right now. And we're going to go over, because we want to get t by itself, simple math, we just divide by negative 9.8 meters per second. Alright, so then this is very simple. We get negative 6 over negative 9.8. I'm going to skip, cancel out the negative. We get, bring this down over here. We get to 6, 9.8. This will give us 0.61, which means that this is actually t squared equals 0.61. So then if we take that, this is 0.61. We just move the t over, square root it. We need a positive number since we can't have a negative value for time. That equals 0.782 seconds. Sorry, up there, I was just confusing the two. I was skipping a step. Alright, so now that we have this information, we've technically solved. Now, you've seen me move this problem B like down a few times. How long will you be in the air? Well, we basically just solved that question right here, funnily enough. In solving question A, we've basically done question B. So, if you really want to do it, we'll just skip to question B really quick. 0.782 seconds is how long he's in the air. Now, if we come back up here, this is still question A, by the way. We're still trying to solve question A through all this information. So, we are going to now do 0.782 seconds. Now, this is a very simple task, right? Because it would take 0.782 seconds for him to fall from... sorry, that was the wrong thing. For him to fall from here, from this position to here. That means it has to take, and he will land on the saddle, and we're trying to find the position of the saddle from the person. That means in the time he's falling, the car, or the horse, is traveling to him. So that means that if the car is traveling 10 meters per second away, and this falling has to be equivalent to how far the car is away, so that when they arrive, this is exactly at 0 right below him. All we have to do is multiply it by the acceleration. So its acceleration is 10 meters per second, and we just multiply that by 0.782 seconds. And look at that, our units cancel out, and we get 10 multiplied by 0.782. And just remember that, I'll bring it down here, multiplied by 10 meters per second. And we go to 7.82 seconds. Sorry, wrong, 7.82 meters. And that's the question A. Because since it takes 0.82 seconds for him to fall, if you see this blue arrow right here, let me try and get rid of a few things. Let me just go through it one more time. If it takes 0.782 seconds to fall from this distance to the saddle, let's just put in this card over here, then it will take 7.82 meters for this car to travel here in the time he's falling, so that they both hit each other, so that he lands on the car. Now, this is represented by this kinematic equation, which I hope everyone understands. This is the second kinematic equation in the AP Physics 1 equation chart, where since we don't have an initial distance and no initial velocity, this is just 0, and we multiply by 1/2, multiply the acceleration times squared. So you see here we did exactly that. We, for the change in x, we do -3 meters per second, and then we equal that to 1/2 equals -9.8 meters per second squared, t squared. Now, -9.8 meters per second, since I'm defining positive in the correct y value, in the standard y value coordinate, and we multiply these by 2, we get -6 over 9.8, and then negatives cancel out to 6.98 equals 0.61. Remember, this is all still equals to t squared, since we just moved the numbers over. T squared equals 0.61. We square rooted 0.61. This is by the way in seconds. 0.61. We get 0.782 seconds. That is the answer to question B. And then we multiply 0.782 seconds by 10 meters per second, the velocity of 10 meters per second, in order to equal 7.82 meters. So that, and then we got how long is he in the air. So we got the question A and B by using kinematic equation number 2 on the AP Physics 1 equation chart. And we were able to use 3 keywords: sitting, vertically, and initially at 3 meters per second in order to solve the equation. That's been question 67, page 51.